The Hubble Space Telescope is one of the most famous spacecrafts currently in orbit around Earth. Apart from their scientific importance, the spectacular images it has produced have impacted millions of people, inspiring them by revealing the mysteries of the cosmos. From the pillars of creation to the comet fragments of Shoemaker-Levy 9 on their way to hit Jupiter, the HST is now in orbit for 35 years, but not everything went smoothly, such as the imperfect main mirror, resulting in blurry images. Without servicing and life extension planning, the Hubble Space Telescope would not have been able to operate its designed lifespan of 15 years, let alone the current 35 years. So, in this video I want to dive a bit into the servicing and life extension of the Hubble Space Telescope. To understand the complex task of maintaining the HST, I want to first give a short overview of the system design, since many of the components were swapped, replaced, or refurbished over the 5 Space Shuttle service missions. Hubble is a Ritchie-Chrétien telescope with 2 mirrors. The 2.4 meter in diameter primary mirror is a concave one and reflects the light to the smaller 30.5 centimeter and convex secondary mirror, after which the light is focused through a hole in the primary mirror. This light is used by different instruments to obtain scientific data, such as multiple cameras and spectrographs. There are also 3 interferometers on board, the so-called fine guidance sensors. Those serve a dual purpose. One of them can be used as a scientific instrument, which can measure the angular diameter of the star and the position. The other purpose is the pointing control. They are the most accurate pointing sensors of Hubble, locking on so-called guide stars, enabling a tracking performance with no more than 0.007 arcseconds of deviation. To visualize this is the same task as pointing a laser to a 530 km away target while not moving the point outside of a 2 cm circle. But there are some less accurate sensors too. There are also 3 core sun sensors, magnetometers, 6 gyroscopes and star sensors, which complete a full stack-up of coarse to fine pointing measurements. To actively turn the telescope, 4 reaction wheels are used. To desaturate the wheels, 4 magnetic torquers are also present. Hubble has 2 solar arrays, generating the power to run it and charge its 6 nickel hydrogen cell batteries. The power is distributed through the power control unit, which also contains switches to toggle certain subsystems, as well as some fuses to protect them. To communicate with the ground directly, or more commonly via the TDRS tracking and data relay satellites, multiple antennas are used. The omnidirectional low-gain antennas receive the commands, while 2 dish-shaped high-gain antennas can send high amount of data back to the ground, like the images and scientific data. Now that we know the core components of Hubble, we can cover the service missions. They were planned and unplanned missions to repair and upgrade the HST using the Space Transport System, also known as the Space Shuttle. In total, 5 missions were flown between 1993 and 2009. I won't go into all of the details and jobs the crews did during their visit to Hubble, but the most important with a focus on the maintenance.
5, 4, 3, 2, 1,
0.
and we have liftoff. Liftoff of the Space Shuttle Endeavour on an ambitious mission to service the Hubble Space Telescope.
Starting with SM-1 in December of 1993, with the launch of STS-61. Over 10 days and a total of 35 hours and 28 minutes of spacewalks, the new instruments and systems were installed. Like mentioned in the intro, Hubble had an issue with its primary mirror. The problem was a mirror that was too flat in the center, creating spherical aberration. Spherical aberration is the effect that the light rays do not intersect in a single point, but rather in a line perpendicular to the focal plane, resulting in blurry images. To fix this, the COSTAR or Corrective Optic Space Telescope Axial Replacement had to be installed. This module optically corrects this for the axial mounted instruments. Also, the wide field planetary camera was installed, which could compensate the flawed mirror. But more maintenance was also completed. The solar arrays were changed, since the transition from cold to hot temperatures resulted in a flexing or jittering in them. In the short 3.5 years in orbit, already 3 of the gyroscopes failed. Therefore, 2 of the rate sensing units, or RSUs, were replaced. Each RSU houses 2 gyroscopes, so that after the mission, Hubble was left with 4 brand new gyroscopes. Also, some subsystems were changed, the magnetometers were added, and 4 fuse plugs were replaced. And in the end, orbit maintenance was performed. Since Hubble is in a low Earth orbit and there is a small residual atmosphere there, it is affected by drag, as we can see in the data from 2022 to 2025. The semi-major axis, so basically the height of the orbit, is slowly decreasing. So, to prevent Hubble from deorbiting, it needs to be boosted back into a higher orbit. Since the telescope has no thrusters, the shuttle orbiter, as part of the service mission, used their thrusters.
1. Ignition and liftoff. Discovery now on its way to service NASA's Hubble Space Telescope.
The second service mission in 1997 mainly swapped one of the cameras and one of the spectrographs. But some additional hardware replacements were also performed. First, one of the fine guidance sensors was replaced since it showed some mechanical wear. A solid-state recorder replaced an older engineering science tape recorder. The new recorder has no moving parts, thus making it not susceptible to mechanical wear. But the new technology has 10 times the storage capacity. Finally, one of the reaction wheel assemblies was replaced with a refurbished spare. The third mission gets more interesting, since it was actually 2 separate missions, SM3A and SM3B. Originally, SM3 was scheduled to do preventive maintenance, but 3 and later a 4th one of the gyros failed, which forced Hubble to stop capturing images.
1. We have booster ignition and liftoff of the Space Shuttle Discovery on a mission to repair the Hubble Space Telescope as we venture into the 21st century.
Therefore, SM3A launched on December 19, 1999, nearly half a year early than the long-planned service mission. Of course, its main focus was the replacement of all 6 gyros to get Hubble back into a working state. Additionally, the next replacement, fine guidance sensor and solid-state recorder were added. The aging spacecraft computer was replaced with a brand new one, based on the Intel 80486, which is 20 times faster than the old one. Also, the batteries are showing some wear. So, to prevent overheating, the voltage, temperature improving kits were installed in order to lower the battery's maximum charging voltage. Finally, an S-band transmitter was replaced due to a previous failure on one of the units.
And liftoff of Space Shuttle Columbia to broaden our view of the universe through the Hubble Space Telescope.
With the launch of STS-109, the second part of the service mission 3 began on the 1st of March 2002. The solar panels were replaced again after 8 years since radiation and orbital debris degraded them. The new ones are 2/3 of the size of the old ones, but provide 20% more power. Notably, they do not roll up like the old ones, but rather fold in 2 parts. A new power control unit goes hand in hand with the new solar panels, so it was also replaced. Additionally, a reaction wheel assembly was swapped out and a cooling system for an infrared camera and spectrograph was replaced, which failed in 1999.
6, 4, 3, 2, 1. And liftoff of Space Shuttle Atlantis, a final visit to enhance the vision of Hubble into the deepest grandeur of our universe.
The final mission to Hubble, carried out by the orbiter Atlantis, launched in the middle of 2009. It is the 5th and final service mission. First, all 6 of the batteries were replaced, leaving Hubble with a total of over 450 amp-hours of capacity. The Wide-Field Camera 3 was installed, replacing the previous Wide-Field Planetary Camera. The new one is unique due to the wide-field panchromatic nature. Also, the rate sensing units, so all 6 gyroscopes were swapped once again. COSTAR, which I mentioned was installed during SM1, was replaced by the Cosmic Origin spectrograph. The advanced cameras for surveys was repaired by replacing a circuit board and adding a new power box. Also, the Space Telescope imaging spectrograph was repaired in a similar manner. The fine guidance sensor 2 was replaced, and in the end the soft capture mechanism was added, which allows future vehicles to dock with Hubble, enabling a safe deorbit procedure. As may be noticed, the gyroscope failed a lot on Hubble. So, after 1999, when the telescope was not able to run for a brief amount of time, a new contingency plan was created. The True Gyro mode. Like the name suggests, it allows Hubble to run with only 2 instead of 3 gyroscopes. Later, also a one gyro mode was conceived. They both work in a similar way, utilizing other sensors to fill the gap of the missing ones. The pointing operation becomes a multi-step process. First, the magnetometer, sun sensors, and the remaining gyroscope will point Hubble to within 10 degrees of the target. Then the star sensors take over and with the help of the last gyro move the telescope onto the target with a tolerance of just 1 arcsecond. At the end, the fine guidance sensor can lock onto a guide star and hold Hubble onto its target within just 10 milliarcseconds. But why did the gyroscope even fail? A small wire, the so-called flex lead, which carries data and power into the mechanism, corrodes, bends, or breaks over time, leading to the failure. To prevent further wear on some of the gyros, working ones are sometimes shut down to preserve them for a later point. This is what is happening at the moment too. There remain only 2 fully functional gyros, and the one gyro mode is active to keep the other working one as a spare. This, however, reduces the observable sky in half for any given point in time, and also decreases Hubble scientific productivity by up to 25%. So how about new missions to repair and reboost the HST? There were actually some talks and studies about a private SpaceX Dragon mission to the HST. The goal would be to boost Hubble back into a higher orbit and do maintenance, probably with a focus on the gyroscopes. However, NASA remains cautious, since a lot of risks are involved. Not only risking the remaining life of Hubble, but also the lives of the Dragon crew. Docking with the HST or the International Space Station are vastly different. The ISS has equipment for easier docking, Hubble does not. Also, the Crew Dragon is a lot smaller than the Space Shuttle around which Hubble was built. Hubble was designed to be repaired and upgraded over time. Without this, the HST would have been only a small piece of what it is today, producing unsharp images and probably not able to point anywhere due to the broken gyroscopes. Hubble's life was extended a lot from the planned 15 years, which is due to excellent engineering and planning. But the spacecraft which carried out these tasks does no longer exist. So, at the moment, NASA expects Hubble to operate into the mid-2030s, limited by the degrading orbit height and the failing of its pointing control.
Chain is armed. Sound suppression water system armed. T-minus 10, 9, 8, 7, 6, 4, 3, 2, 1. And liftoff of Space Shuttle Atlantis. A final visit to enhance the vision of Hubble into the deepest grandeur of our universe.
Bypass across the board, Scooter, no action.
Houston now controlling, Atlantis on its way.